Find and classify all the equilibrium solutions to the autonomous differential equation we have here. So classify, so that means we're looking for stable, semi-stable, and the last one would be unstable. So we'll need the equilibrium solutions, but we also need to classify them. And the best way to do this is quickly sketching a phase plot for our autonomous DE. So I think we could probably just get away with doing it up here. We don't need a separate sheet of paper for this. Okay, so first we need to find the equilibrium solutions. That's not that bad. When is the derivative equal to 0? So we just put 0 in there, and then we say, well, what constant, what y values make this true? And we can pretty quickly see, okay, y is 0, y is 1, and y is -5. So we'll just sort of plot them here, -5, 0 here, and then 1 here. Okay, so those are the equilibrium solutions, but how do we bring a phase plot into this? So a phase plot is just going to be the graph. So here's the y, and then this axis here is the y prime. We just plot the graph y prime equals this expression here, y times y minus 1 times y plus 5. Okay, and okay, so let's get to sketching our phase plot. So this is the height and these y values. Even though it's the output of the function that solves our differential equation, we're sort of treating it like the independent variable here. It's the horizontal variable. This is a cubic. Right? It's going to go through these roots or these zeros. And we can see, okay, it's a cubic, and the y's here are all positive. So it's a cubic with a positive leading coefficient. And so it's going to look something like this. So we can quickly sketch. It doesn't have to be super accurate, but our phase plot is going to look something like this. And once we have the phase plot, then we can, I like to just come along with arrows, we can come along and classify. So whenever your graph is below the axis, the horizontal axis, then that means your rate of change is negative, and so you're decreasing, and you'll be going away. Your y values will be getting smaller and smaller, or more and more negative. So you'll be moving away. Anytime we're above the horizontal axis, then the y prime has a positive value, and so we should expect the y values of our function to be increasing, which means moving to the right. Right? Y value is getting bigger. Well, here's our y-axis, so we're moved to the right. That's how we increase. So again, we're below here, so we move to the left, and then above, we go here. All right, so having done this, how can we classify each of these? So -5 and 1 are both unstable because no matter what side you're on, you're moving away from it. Okay, so -5 and 1 are unstable. And 0 here, everything, whether you start on this side or that side, everything is headed towards 0. So 0 is a stable solution. We don't have any semi-stable ones, but a semi-stable one would be where on one side you're headed towards your solution, and on the other side you're headed away. So it really depends on what side you start. But no matter what side of 0 you start, everything's tending towards 0. No matter what side of 1 or -5 you start with, your solutions are taking values that are getting further and further away from those steady states there. So here's our final answer. We have 3 equilibrium solutions, -5, 1, and 0. -5 and 1 are unstable. 0 is a stable equilibrium solution.